Hello, everyone. This is a video presentation of our most recent work on L2M, Mutual Information Scaling Law for Long Context Language Modeling. Long context language modeling capability is crucial in the current era of generative AI. It underpins many important applications, including reasoning through long chain of logic, maintaining consistency in long writing, understanding large code bases, and keeping track of an extended conversation. However, the current understanding of the trade-off between cost and performance in long context length modeling is very limited. While transformer architecture has shown superb performance in many tasks, the inherent quadratic computational cost is a major hurdle for long context length modeling. To circumvent this issue, many alternative architectures have been proposed. This includes linear attention, sparse attention, state space models, and some other compression methods, or even OCR. However, although these new architectures significantly reduces the computational cost, they inevitably hurt the long context length performance. In this work, we propose a new universal framework for understanding long context length modeling based on a notion called bipartite mutual information, which also informs the design of efficient and effective architecture for dealing with long sequences. Consider a distribution of natural language corpuses. Suppose we fix the sequence length to L and then split each into two halves, labeled X and Y. The bipartite mutual information is just the mutual information between the two halves over the whole distribution. Using our newly proposed LLM-based mutual information estimators, we observe that the bipartite mutual information grows as a power law with respect to the sequence length. This observation is confirmed using various estimators on multiple datasets and across different cuts. This bipartite mutual information exactly quantifies the amount of information that must be retained from the random variable x in order to correctly predict the conditional probability of y given x. Therefore, it is crucial for large language models to be capable of capturing the power law growth of mutual information in order for effective long context modeling. To understand how large language models capture the mutual information, let's first get familiar with a notion called history state. Consider a large language model that takes input tokens and output conditional probabilities of the next token given all prior tokens. It is important to note that the dependency of the next token from the prior tokens are not explicit in large language models. One can identify a set of latent variables that indirectly passes the information from the prior tokens to the later tokens. More explicitly, notice that the conditional probability of W4 given W1, W2, and W3 is actually the conditional probability of W4 given Z2 and W3. We define the history state to be such collection of latent variables that summarizes the past information and passes them to future tokens. To make the notion more clear, let's understand what the history state is in transformers. In a transformer, the input is turned into the query, key, and value, and the query acts on the key-value pair to obtain the attention output. Notice that for later tokens, the query must also act on all prior key-value pairs in order to obtain the correct output. In other words, all the past information is summarized in the key-value pairs, which are therefore our history state in transformers. The history state of a state space model is much more clear as it has an explicitly recurrent state that summarizes past information and passes it to later tokens. Therefore, the recurrent state is exactly the history state we are looking for. We now understand the history state and therefore can analyze the necessary requirements for large language models to effectively model long sequences. In particular, for the bipartition we discussed previously, notice that a large language model models the conditional distribution of y given x via the history state z. In our paper, we prove that the maximum bipartite mutual information that a large language model can capture scales in the same rate as the size of its history state. Therefore, a large language model architecture is effective for long context modeling only if the scaling of its history state size is faster than the scaling of the bipartite mutual information in natural language, which is a power law in the form of L to the beta, as we previously observed. Our theoretical framework is rigorously verified with experiments. The details can be found in our paper. Our framework has profound implications. For the vanilla transformer architecture, its history state, which is the collection of key-value pairs, grows linearly with sequence length, which is faster than the power law of the bipartite mutual information growth in natural language. However, as our theory suggests, a sublinear scaling of history state could still be sufficient for effective long context modeling as long as it is greater than L to the beta. Due to the overprovision of the growth rate, transformer results in a quadratic complexity, which is less ideal and making it difficult to scale to super long sequences. State space models, on the other hand, although has a linear time complexity, but its history state size is bounded by a constant determined by the network size. This means that regardless of the network size, a state space model will eventually fail to capture all the necessary multi-token dependencies, and therefore fails to effectively model long sequences. Our theory suggests that we don't need a linearly scaling history state. Ideally, one may postulate a network architecture whose history state growth rate is just above L to the beta, which is the growth rate of the bipartite mutual information scaling of natural language. This could result in much lower time complexity compared to transformers, achieving slightly superlinear time complexity, or possibly even linear complexity. Our theoretical framework allows for a foundational understanding of long context language modeling and provides insightful and practical guidance in designing large language model architectures that perfectly matches the bipartite mutual information scaling law and allows for effective and efficient modeling of long sequences.